We have already discussed the design of the input stage of the active antenna, but not in the context of a negative feedback amplifier. We have discussed it in the context of just having an CS stage connected to the antenna and then discuss the noise performance. If we discuss it in the context of negative feedback, I'm sorry for putting all the lines immediately here, I forgot to split it out, then we must consider the influence of the feedback capacitance on the noise performance. And I hope you remember that with this structure, it is as if CF is in parallel with the input of the amplifier. So in parallel basically with the source impedance CA times L. And this we have to account for, of course, during design. Because now the optimum for the lowest 1 over f corner frequency, we already found that we achieve the lowest 1 over f corner frequency if the input capacitance of the transistor equals the source capacitance. But now we have to consider also that CF is in parallel with the actual source CA times L. So we need to make CISS a little bit larger. I will show you in a while the optimization of SliCap. I think we did this already, but now it's completely with all the influence of the impedance in parallel with the signal path. And with a width of 1.2 millimeter, length of 1.25 micrometer and drain current of 1.4 milliamp, you will achieve a noise floor equivalent at the input of the antenna in E field of 5.3 nanovolt per meter per root of hertz, which is a little bit more than required, but you can just increase the current to tune it, because this algorithm is not really iterative, it's just a feed forward calculation. The corner of the 1 over f noise turns out to be 34 kilohertz, what we can make, and that is good enough because we need 100. We can reduce, of course, the floor noise by increasing the current, and I will show you that other combinations of W and L and the drain current are also possible. But the smaller you make the width, the more drain current you will need, because you need to make it longer as well. So there are two files, and you can download the zip from from Brightspace. The Python and the LT-Spice. The LT-Spice is just to show you a few things that are happening with a model, with this BC model that we use. And but of course, basically you could do all the noise design and the signal path design in SliCap. And only at the point that we need nonlinear stuff like the drive capability, or we want to analyze the distortion, then we need to go to LT-Spice. Sorry. So the input stage that we will discuss with SliCap is this file, and it has the antenna model. So there was, in the first week of the course, there was a link to an article that described a lump element model for a short rod antenna, and this model is what we are going to use, so we can just set the width and the diameter and the length of the antenna, and we have a nice expression for the capacitance at low frequencies. We will determine then the length, the drain current, the width, and the noise and the antenna specifications. So here is the circuit that we use. And now you see indeed that we have the noise sources of the MOSFET, but we have placed in parallel with the source CF, this feedback capacitance, because it is as if, for the noise, as if it is in parallel with the source. And maybe you see immediately what will happen if you shift Vn towards the direction of the electrical field, so towards left. Then you cross the intersection point of C1 and C2, and it splits in two correlated sources, and you have to account basically for both sources, which means that effectively Vn is multiplied with a factor that is set by 1 plus the ratio of the capacitors. So you can do this yourself because we have discussed this extensively in the third year. And if you're not familiar with it, please go to the homologation program and study the influence of impedances in series and parallel with a signal path on the noise performance. And there you see this step by step explained. So if we do this with Python, and I will show you in a while, then I listed a few widths, 1.2 millimeters, 900 micrometers, and 600 micrometers, and it calculates the length and the drain current and all the other things. So the spectral density, it is like 2.8 times 10 to the power of minus 17, and it should be 2.5. It's a little bit more, and that corresponds with the 5.3 nanovolts per meter per square of hertz. That should be 5. But okay, increasing the current a little bit, and the whole thing is according to spec. The most important thing is that the corner frequency of the 1 over f noise is about 30 kilohertz, a little bit more, and that's really much lower than we need. So there is still reserve in the design. We are not dealing here with a showstopper, and that is at this stage what we want to find out. Since CF is not very small, it's 2.5 PF, and the antenna, it's about 3 PF with the antenna model, and the antenna capacitance was 6 PF. We have total input capacitance of about 9, a little bit more. So here it is 10 PF, and you also see the inversion coefficient of the transistors listed, which means that if you make the transistor narrower, you have to go to a higher inversion level.